speaker is Indrajit, who's a researcher at HP Labs. He got his PhD in computer science from UT Austin, and he'll be talking about R for large-scale incremental processing.
So I'm Indrajit from HP Labs, and today I'm going to talk about how we can write complex applications which continuously analyze data. And it's not necessary that you should have a background in R or MATLAB. R especially is open source and statistical software. So let me start with the example of Netflix. Netflix has millions of users and thousands of movies. And these users rate the movies, then there's a recommendation algorithm which suggests you movies. Now, not all the time the movies that are suggested are great, but there are two things which I want to draw your attention to. The first part is, look at the algorithm that they are trying to run. It's a complex algorithm. It's not just searching or sorting. In this case, it might be SVD, which is matrix factorization. The second part, which also ties into the keynote, is people want to do incremental processing because the data is changing, it's evolving. New ratings are being added, and the recommendation algorithm has to take into account new ratings and give you new suggestions quickly. Now, even though I've started with the example of Netflix, complex algorithms are really pervasive. So they're at Google, they're indexing the web, and they run PageRank. There are other companies, social networking companies like Zynga, Twitter, who would like to run graph algorithms like vertex centrality, just to get to know who are the important people in their graph, whom they should target their advertisement, or whom they should try to retain. So one of the key questions or key challenges going forward is, how do you express these complex algorithms, specifically when the amount of data that you want to crunch on is really large. So you want an easy way to express these algorithms and also run in a parallel and most likely in a distributed manner. But that is not the only challenge here. Not only do you want to express these complex algorithms, but you also want to get fast results with low latency. And by low latency, I mean incremental processing, so that you don't start from scratch. Some new data comes in, you process it, and you get the updated results. And this is very close to the spreadsheet-like computation that we are used to. If a cell changes in let's say Microsoft Excel, and there are other cells which are dependent on it or using that value, then they get updated automatically. So you want something of that flavor, but for algorithms which are complex, such as machine learning and graph algorithms. The good thing about the incremental processing is that you get low latency processing, so you get fresh results. And this is the place where the industry is moving towards. For example, a couple of months ago, Google updated its algorithm to make sure that you get fresh search results. But if you look at the current systems which are used for large-scale analysis, then they are not adequate for these two challenges. If you look at MapReduce Ride, they have made distributed processing very easy. For example, you can take a program, run it on hundreds and thousands of machines all permanent. But they are not really suitable for machine learning graph algorithms. Similarly, look at Google Berkeley, they can do incremental web indexing. And as Fabien Mike said, you have continuous query systems which can take SQL, they can run it through over lots of fast events, or event series. But they are not really suitable for machine learning and graph algorithms. Just like SQL has been a success story for databases, what you need is a language interface, a runtime system, which can do the same thing, but for machine learning graph algorithms. So our approach is, why not use linear algebra? So why linear algebra? The reason is a lot of machine learning graph algorithms can be actually expressed using linear algebra operators. And in this talk, when I say linear algebra, you can think of linear algebra just like matrix multiplication, that's matrix operations. So if we had a system which could do distributed linear algebra, then you can express a lot of complex algorithms in that system and have them parallelize very easily because they could reuse a lot of these operators that are already implemented. For example, if you take the case of PageRank, it's a dominant eigenvector of the graph, web graph. And if I represent the web graph as G and the PageRank vector as P, then a very simplified way to think of PageRank is that you multiply G into P, which is a matrix into vector multiplication. You do it iteratively till convergence, and you get the PageRank vector. But this is not only for PageRank. You can actually do a lot of graph algorithms also in this framework. For example, take the case of breadth first search. We generally don't think of doing breadth first search using matrix multiplication, but take the example of 5 vertices which are there in this graph. Let's say G is the adjacency matrix representation of this graph, and let's say that X is the initial breadth first search vector. So X is all zeros except for the first position, which I say is the source vertex. Let's say A, and you want to do breadth first search starting from A. Now, if you multiply X with G once, then you get all the neighbors of A. If you multiply it once more, you get all the vertices which are up to 2 hop distance away. If you multiply once more, you get to the whole graph, which is all the vertices which are up to 3 hop distance away. So this is just an example. You can do many more things in it using linear algebra. So linear algebra can be a common abstraction for writing a lot of complex algorithms. For example, eigenvectors, they're pervasive. If you look at page rank, triangle counting, graph partition, all of these algorithms use eigenvectors. A lot of graph algorithms like shortest path, breadth first search, centrality measure, all of them can be written using linear algebra operators. And so can clustering, the usual k-means, or recommendation algorithms, which I started with. So in HP, our approach has been, why not create a system for large-scale linear algebra? And the system is called Presto. By using linear algebra, what we can do is we can express and efficiently implement a lot of machine learning and graph algorithms. But that's one part. The second part is not only can you express a lot of algorithms, but you can actually get the results out with low latency because we rely on incremental processing. So in the rest of the talk, I'm going to tell you a little bit about the programming model. Then I'm going to tell you a few system challenges. Of course, this is not a fully technical talk, so I'll just touch upon a couple of them. And in the end, I'll show you some results and applications that we have already implemented in the system. So Presto has only 3 things. It has a single data structure, which is a distributed array. It has a couple of language constructs like on-change and update, which allows you to write incremental algorithms. And finally, it has efficient support for sparse data, which is quite important. So at a very high level, all the data in the system is represented as arrays. These arrays are partitioned, they are stored across different servers. All of this is in memory. And there is a computation which occurs on these different servers. And it might be iterated. And there could be exchange of data between these iterations, and you finally get the result out. So there are 2 things to take note of here. Really, the first thing is that you distribute the array so that you get scalability, but you also get parallelism. The second part is the system actually takes care of a lot of partitioning for you, and it can optimize the partition so that you get better results or better performance. The second part is incremental processing. So whenever data changes one of the components, here in this example, just one of the partitions, then the corresponding task is re-executed, and you get the final result. So you don't do a re-evaluation from scratch. You just update your corresponding elements in the array, and you get the final result out. Of course, this is a very simplified view because most of the algorithms are iterative. So after a few rounds, you probably have many more tasks which are re-executing on the data. But most of the time, it's on the new data. Here is a simple example of how to write programs in Presto. You don't have to look at all the code, really. I'll step through a few of the main components. The key point is that Presto is based on R. So there are certain abstractions in Presto which we have to implement. We didn't start from scratch. We didn't create our own language. Rather, what we did is we took R, which is a static software which a lot of people use anyway, and it's also an array-based language, and we extended it to include the new components. So this is an incremental PageRank code. What is really happening is this lower part of the diagram, which is you have a PageRank vector, which is partitioned and distributed. Each of this P1, P2, Pn by S are the different partitions. And each of these partitions is calculated in parallel by getting the different partitions from a matrix and a couple of more vectors. Just to step through the code, initially you describe or create the distributed arrays by the clause darray, which is very similar to arrays or the construct array in R, for those who are familiar with it. Then you say that whenever this matrix M changes, then you need to recalculate the PageRank. So you just say on change of M. Then you create a parallel loop which allows you to run these functions in parallel over a cluster. and you pass the correct partitions or the data to the function. And finally, you perform the page rank computation and update. What you see in this code is that it's really familiar for people who are using R or even MATLAB. It's close to that. But unlike R, this is distributed. It can do incremental computations, and it's also fault tolerant in nature. So there are multiple systems challenges if you want to get the system first running. For example, you have to take care of caching of data. You need to co-locate all the arrays, both within the same machines that you want, or the partitions of the arrays on the same machine. Then you have to take care of fault tolerance. But I don't have time to talk about all of it. I'm going to just touch on two things which you need to solve to get this to work. The first thing is sparse data sets. Most of the real-life data sets are sparse. If you look at the graphs that you want to run up, they have less than 1% of the total edges. And if you run these computations, which is really a structured computation, whenever you do linear algebra, it's a structured computation, on sparse data set, you need to partition data. And if you do a naive partitioning, it can cause a lot of computation and communication imbalance. For example, you could have a task which has one partition which has lots of elements, so it's going to be really slow, compared to other tasks which have very few elements to process. So if you look at the overall picture of the whole system execution time, then it gets really slow. So you need to handle this. And just to show you that this is a real world case and not something that I'm making it up, we looked at different data sets. We looked at graphs from LiveJournal, from Twitter, from the web graph itself, and even the Netflix price data. And if you just take this data, map it to a matrix, and then create 100 blocks out of it. This is simple, like the first block becomes 1/100th of the rows and 1/100th of the columns. You'll see that the densest block, which is on the right-hand side, could be as much as 1,000 times, or it could have as much as 1,000 times more number of elements than a sparse block. So there's a lot of imbalance in real data sets. So at a very high level, the way we solve this is that Presto can dynamically create partitions and change the partitions during the execution of the algorithm. So we profile the first few partitions, figure out what are the bottlenecks. There could be certain partitions which are too big, or too big in the sense too many elements in it. A certain partition that have too few elements in it. And you can dynamically merge them or break them apart just to get balance in the system. So the good thing is you don't require any changes from the programmer. Of course, we have to specify a few invariants to show that to make sure that the correctness is maintained. And in some of the experiments that we did, depending on the algorithm, you can get up to a 2x improvement in the performance. The second thing that you want to do is you want to express your dependence of the program on data, so that whenever data changes, the program is re-executed, or certain components of the program is re-executed. The other challenge is the data itself is dynamic. So there's new data, there's old data, and there's a program which is running on it. So you have to make sure that the program executes on a consistent version of the data or consistent view of the data. The way we solve it is, I showed you already an example of onChange, which allows you to express dependence. So you can say that whenever the array A, B, and C change, then perform this computation. You can also say that this is how I want the information to be propagated in the system. And there are certain other mechanisms like memoization, which helps you to reduce the amount of tasks that you are redoing. And finally, we use versioning of arrays to make sure you have a consistent view. These are all very at a high level. If you want to know or get more information, then I'm going to talk later on during coffee break. So let me just quickly go through a few applications that we have looked at and already implemented in the system. And these include PageRank, triangle counting, the recommendation systems, even graph algorithms like centrality measure, connectivity, k-means, sequence line, a lot of them. And we are continuing to include more of these algorithms in the system. All of these algorithms can be written with less than 140 lines of code. The main idea that I want to give you is that most of these complex algorithms map well into linear algebra abstractions, can easily be expressed in a system like this. And I'll make this one of my last slides, which is a few numbers just to show that it's not expressibility only, but you actually get performance also by using this system. And this is page rank per iteration time on a graph which has about 1.2 billion edges. As you increase the number of workers, which is equal to an increase in number of servers, let's say when you go from 8 to 64, with Presto, which is blue in color, you can finish one iteration in less than 7 seconds. If you compare it with Hadoop, it will take you more than 160 seconds, even with 64 machines. So there is an order of magnitude difference or benefit of using a system like Presto, which is catered specifically for machine learning and graph algorithms. A lot of time I'm going to probably skip this slide, which says that you can do incremental processing, but there is a trade-off between the freshness of result and the resource usage. Just to give a nugget, if you have, let's say, 100,000 of these updates batched together and you process it, you can finish or get the whole page rank value in just 200 seconds, compared to 600 seconds if you were starting from scratch. This is for a smaller data set. Of course, if the batch size increases, then your benefit goes down because it takes up to 300 to 400 seconds. But if you look at the number of times you're running the algorithm, just because every time a update comes, you run the algorithm. So if you look at the total time you're spending, that might be quite high, which is here, the red line. So there's a trade-off between how much resources you want to use versus the amount of freshness you want to guarantee to the user. And these are concerns which will come into play when you want to go towards energy efficiency in the future. Finally, just to summarize, Presto uses linear algebra as the abstraction to write machine learning and graph algorithms. And a lot of these algorithms, which are complex in nature and also incremental, can be expressed very easily in the system. And for most of these algorithms, we know that we are about an order of magnitude faster than Hadoop. Thank you. So I'm happy to take questions.
Does the system have support for higher dimensional arrays, tensors, or does it only partition 1 and 2 dimensional arrays?
No, it has higher dimensional arrays as well. So, but most of our examples actually use 2D arrays, just because the algorithms require it.
Can you explain a little bit more about why do you think this system works better than Hadoop 20x?
Better than Hadoop? Yeah. Okay, so I think the best way to think about this, a lot of these are matrix multiplication operations. Writing a matrix multiplication operation in Hadoop is a pain. If you have to do a join, and then you do an outer product. And even if you don't do all of these, think of what Hadoop does. There's a map phase, followed by shuffle phase to make sure the right data goes to the right reducer. That whole shuffle phase, which is costly, is totally not required in a system like this, if you keep the mapping of what the element and the array indices. So there is, algorithmically, you save on this n log n directly. Of course, there are other problems that creep up, which is the sparsity. If you look at Hadoop-like systems, you can just hash partition the data. And it's fine, because the shuffle phase is going to send the data to the right places, which doesn't work if you use structured processing. And this is where we need to solve it. But this is one example why Hadoop is for these kinds. It's also the case that Hadoop and Dry, these are based on relational algebra. So their focus is not the kind of algebra we want to run. So they are not good for matrix operations. And people have tried to extend, like Hamline and others, people have tried to extend Hadoop for this, but they're still inefficient.
I have a question also. How is it easy? Is it for users to extend and do their own algorithms? So say I want to do a support vector machine update for that.
So things like support vector. So a lot of things you need to realize is you need to first parallelize it. So support vector machines, first you have to tell the algorithm to parallelize it, which you have not. So once you figure that out, then it's easy to express. This system cannot parallelize things for you. But things like PageRank or centrality measure or BFS, these are easy to parallelize. You know the versions. Then it's very easy for you to write an incremental version of it. You just say change the increment over the array changes, we do this. A lot of things are done by the system itself. So you don't, even if you say that whenever this whole matrix changes, just do it. Even if one single element changes, the system can figure out that, okay, the small partitions have not changed. So when I'm doing multiplications, I don't really have to multiply because I already have the old versus normalization.
But in terms of the code base, if you did have something that was parallelizable, is it something as easy as you plug in your own wrapper function
So I'm hoping when you say support vector machines or any other algorithm, you're probably written in this format, which is MATLAB-like format or R-like format. Then it's very easy because you just reuse it. You have to sprinkle a little bit of code. I had an initial slide which showed that if you use R for this MATLAB maybe, then the number of lines of code is less than, let's say, 40 or 50 lines, and close to 140. So there's about 100 lines of code difference, which has to be sprinkled to run the cluster. But it is very manageable. We have had people in machine learning in our group use it. And they find it. Okay.
Maybe one last question?
With your comparison with Hadoop, you had 1.2 billion edges and 96 gigabytes of memory. 1.2 billion edges stored sparsely should take something like 9.6 gigabytes. So it's looking like you've got a huge amount of memory for doing what you need to do.
So
yeah, if you try to do the same thing on, say, a 4 gigabyte machine, where you start running memory problems and the sort of distributed stuff that Hadoop does starts being a bit more necessary. How do you work in that environment?
Right, so the system allows you to store data if it runs out of memory, but don't go by the size of these data sets. So these are data sets which are just a graph, right? In real life, it's not the case. In real life, what happens is you have probably things and the size blows up. But it's really the computation which is taking time, and not so much going to disk or not out of disk. And just to be fair, the Hadoop results are really from in-memory Hadoop. So we make sure that all the Hadoop results on the HDFS actually runs on RAM address. So it's a fair comparison in terms of, so it shows that Hadoop is slow, not just because of disk latencies, but because the programming model is a good fit.
Okay, let's thank the speaker again. And our next speaker is Indrajit, who's a researcher at HP Labs. He got his PhD in computer science from UT Austin, and he'll be talking about R for large-scale incremental processing.
So I'm Indrajit from HP Labs, and today I'm going to talk about how we can write complex applications which continuously analyze data. And it's not necessary that you should have a background in R or MATLAB. R especially is open source and statistical software. So let me start with the example of Netflix. Netflix has millions of users and thousands of movies. And these users rate the movies, then there's a recommendation algorithm which suggests you movies. Now, not all the time the movies. There are other companies, social networking companies like Zynga, Twitter, who would like to run graph algorithms like vertex centrality, just to get to know who are the important people in their graph, whom they should target their advertisement, or whom they should try to retain. So one of the key questions or key challenges going forward is, how do you express these complex algorithms, specifically when the amount of data that you want to crunch on is really large. So you want an easy way to express these algorithms and also run in a parallel and most likely in a distributed manner. But that is not the only challenge here. Not only do you want to express these complex algorithms, but you also want to get fast recipes that assist great. But there are two things which I want to draw your attention to. The first part is, look at the algorithm that they are trying to run. It's a complex algorithm. It's not just searching or sorting. In this case, it might be SPD, which is matrix factorization. The second part, which also ties into the keynote, is people want to do incremental processing because the data is changing, it's evolving. New ratings are being added, and the recommendation algorithm has to take into account new ratings and give you new suggestions quickly. Now, even though I've started with the example of Netflix, complex algorithms are really pervasive. So at Google, they're indexing the web and they run PageRank. Google updated its algorithm to make sure that you get fresh search results. But if you look at the current systems which are used for large-scale analysis, then they are not adequate for these two challenges. If you look at MapReduce Ride, they have made distributed processing very easy. For example, you can take a program, run it on hundreds and thousands of machines concurrently. But they are not really suitable for machine learning graph algorithms. Similarly, look at Google Percolated, they can do incremental web indexing. And as the top by Mike said, you have continuous query systems which can take SQL, they can run it through over results with low latency. And by low latency, I mean incremental processing, so that you don't start from scratch. some new data comes in, you process it, and you get the updated results. And this is very close to the spreadsheet-like computation that we are used to. If a cell changes in a, let's say, Microsoft Excel, and there are other cells which are dependent on it or using that value, then they get updated automatically. So you want something of that flavor, but for algorithms which are complex, such as machine learning and graph algorithms. The good thing about the incremental processing is that you get low latency processing, so you get fresh results. And this is the place where the industry is moving towards. For example, a couple of months ago,